Hello and welcome to lesson 6.4, intersections of lines in 2 space and 3 space. So first off, we're going to take a look at how lines can interact, that is not necessarily intersect, could intersect in 2 space. So these are the 3 cases that we've studied before. You can have one solution, which occurs when you have one point of intersection. You can tell this ideally by looking at the directional vectors if you have it in vector form. You'll notice that they're totally different. You can also notice that the normals are totally different in scalar form. You could also have no solutions. This occurs when you have parallel lines. This you can tell readily from the directional vectors. They're the same, but however the starting points, you're not too sure. They could be similar yet different. But if you look more at the scalar equations, you'll notice the scalar equations, the normals are the same, but the c values are completely different. And in our last case, you can have an infinite number of solutions. This occurs when you actually have the same line. Again, the directional vectors do turn out to be the same. The starting points could be the same, could be totally different. However, if you look at the scalar equations, it's easier to tell that they're exactly the same line. So in 2 space, it's best to actually change it to scalar equation form and then compare them. When talking about 3-dimensional space, you can have a possibility of no solutions, which you can see in your top left. Again, this occurs when you have parallel lines. In this case, you can see that the directional vectors turn out to be the same. But because you can't change the lines into scalar form, you can only investigate it in parametric or vector form. You can also have an infinite number of solutions. Giving you the same line. In this case, your direction vectors also turn out to be the same. The only difference between one and the other is the values of s in the left ones and the values of t are not the same, whereas the values of s and t are the same in the right ones. There's also the possibility you can have one solution, giving you a point of intersection. Again, notice here your direction vectors actually turn out to be different, or not scalar multiples of each other. Or you can have an instance where you may have also no solutions again. This occurs when the 2 lines aren't actually parallel, but they'll still never touch. So these are called skew lines. And again, can happen when your directional vectors are totally different from each other. So in 3-dimensional space, they can interact in 4 different ways. The top 2 occur when your directional vectors are the same or scalar multiples of each other, and the bottom 2 are when they don't. So it can help you narrow down your solutions by starting to look at whether the directional vectors are the same or different, and then use that to figure out if they actually intersect by using see if the x, y, and z values are the same, giving you the same values of s and t. So let's see examples of this. So let's say we have these 2 lines, and I want to determine the point of intersection. Again, realize when it says the point of intersection, not necessarily is there a point of intersection. You have to be careful with it. So let's call these lines 1 and line 2. usually denoted by an L and a subscript. What I'm going to do is I'm going to change line 1 and line 2 into scalar form. So I'm going to choose a normal of 2, 3 for my first vector. Sorry, for my first line. And now I'm going to solve for C. So I get my first line. I'm going to call it equation 1. Now I'm going to change line 2. I'm going to strategically choose that normal to be 1 and negative 2, because that one gives me a leading coefficient that's positive. And now I'm going to figure out the rest of the equation by substituting my point in. And I'll call this equation 2. From here, in order to solve for my point of intersection, and I know there's going to be a point of intersection because these two normals are totally different, I'd probably use either elimination or substitution. So I'm going to take my first equation, leave it as is. I'm going to take my second equation and multiply by negative 2. This way I'll eliminate the x variable when I add the equations. So I get a y value of 8. Now we just take that and substitute it back into one of our equations to solve for x. So I get a point of intersection here. Of 3 and 8. Okay, so that's how you deal with it in two-dimensional space. Let's see in three-dimensional space. In this case, these two lines, you can notice, the normals are totally, but the directional vectors are totally different. Since the directional vectors are totally different, this means you either have skew lines or you can have a line of intersection. So to do this, first take your lines and change them into parametric form. Both lines. Okay, so now that I've got that, realize that the x values and the y values have to be the same in order for there to be a point of intersection. So that means I'm going to equate the x values, equate the y values, and equate the z values. I'm going to take these equations and simplify them for myself. And I get 3 different equations, but 2 variables s and t. If there is a point of intersection, the value of s and t is the same for all 3 equations. If there is no point of intersection, then the values of s and t don't exist. They work for two equations, but not the third one. So, choose any two equations and solve for s and t. So in this case, I'm going to choose equations 2 and 3, and I'm going to solve for s and t. And again, I'm going to use elimination or substitution. So here I find my t value is -3/4. I'm going to solve for s. So I get a value of s as 21/4. So if, again, there's a plane of intersection, then it also fits for equation 1. So we should verify s equal to 21/4 and t equal to -3/4 in equation 1. And if we find one, then we can substitute s or t back into our original equations for line 1 or line 2 and actually solve for the point. So I'm going to first verify. So 3 times 21/4 minus 4 times -3/4. Considering I don't know what this equals, I know it may equal 2, it may not equal 2. I don't know yet. I'm going to figure that out. So don't set it equal to 2. So this equals 75/4, which does not equal 2. Therefore, these lines are skew. And do not intersect. So, no solution. Okay, so some definitions that go along with this. If you ever hear the term consistent set of solutions, this means that a system has an infinite set of solutions or one solution. Consistent just means it has a solution. Whether it's infinite or one, doesn't matter. If it's inconsistent, then there is no solutions. If the lines are said to be distinct, then they are said to be parallel. If lines are said to be coincident, then they are the same line. So you may hear these terms or definitions when talking about or looking at what kind of solutions you're looking for. Okay. So last thing that we're going to look at is how to determine the minimum distance between two skew lines. So in order to figure this out, I'm going to draw two skew lines here. Now the minimum distance between these two skew lines turns out to be a line that's orthogonal to both of these. The only issue is we have to find out that distance. So we know how to find something that's orthogonal. We can find a normal that's orthogonal. The only issue is, how do we find the length of that item? Well, what we can do is we can choose any point on one of the lines. I'm going to call it P. And I'm going to choose another line, point on another line, call it Q. And I can create another vector. Let's call it PQ. Well, if I find the magnitude of the projection of PQ onto the vector n, that would give me my minimum distance. Oh, if we remember projection, that's PQ dot n over n dot n times the vector n. Well, I can change these magnitudes to be PQ dot n alone. N dot n is the same as magnitude n squared, and the magnitude of the vector n is still just the magnitude of n. This can simplify further by canceling. To this expression. Okay, so now let's find the minimum distance between two skew lines. So here we know that these are two skew lines. We're going to find the minimum distance. So first off, we know our directions. We can figure out a normal for this by taking the cross product. Okay, so pause your video and work out your cross product. Okay, I'm going to work out my cross product here. I get -2 plus 3. I get 6 plus 1. And I get -1 minus 4. So I get my normal as 1, 7, and -5. I can also figure out my vector PQ. My vector of PQ is just the vector from one starting point to the next starting point. And doesn't matter which way you subtract them. So in this case, my vector PQ turns out to be 3, -4, and -3. So now to figure out the minimum distance, I take PQ, dot it with n, put that over the magnitude of n, and solve. Sorry, finding the magnitude of the wrong vector. Remember, the numerator has to be in absolute value signs, so it's actually going to give you a positive value no matter what you do. Because distance is always a positive value. So numerator turns out to be 10. Denominator turns out to be the square root of 75, which you can simplify to 10 over 5 and root 3. So this is 2 over root 3, or if you want an approximation, about 1.2 units away. And thus concludes this lesson.